Hello, everyone. Welcome to today's brand new episode of Corecast. I am your host, Tim.
And I'm Mikey.
This is Sahil. Welcome everybody to a brand new exciting episode of Corecast. If you haven't already, do join our Discord channel so you can ask us questions there. And if you're watching on YouTube, where we do this every Tuesday at 5 p.m. Pacific, 8 p.m. Eastern, do ask questions during the episode so we can get and answer them. So without further ado, Tim and Mikey, both of you, there was some interesting news that Quantum Magazine, if I remember correctly, announced about some wormhole created on a chip, like a computer chip. And this was like collaboration between Google, Caltech, Fermilab, MIT. I might be butchering some of the organizations, but it was just a large collaboration. So I guess like it seems monumental, but I wanted to I wanted during this episode for us to get down and dirty into it and say like, is this hype? Is this real? Like, what's going on with that? So I guess Tim, let's take a step back and say what is a wormhole for starters? Like, I mean, I think of like Interstellar, the movie, but like, how do you think about it?
Yeah, I would say the hype is there. Some things are real, some things are more hype, but it's definitely a significant achievement. Like all the buzzwords are there: Google, quantum computing, AI,
No,
physicists.
screw those buzzwords. Let's talk about independently of
Yeah,
that.
yeah. Forget about buzzwords for now. Okay. Let's focus on the keywords right here. The keyword is wormhole. Okay. Um, Well, let me just go over what people usually think of what a wormhole is. What a wormhole is popularized, I guess, is it like through Einstein's kind of work? It's kind of like a space, some kind of like a tunnel, some kind of like a magical tunnel. Usually, it's linked to a black hole, and obviously, if you have seen the movie Interstellar, that's kind of a really popular depiction of it. It's kind of a region of space time where you can enter kind of freely and an exit somewhere else that's kind of completely brand new. It could be a different universe. It could be a super far away part of our own universe, and that's kind of what the science fiction imagination is. A wormhole is a place where you can enter and exit and travel great distance in space and time, right? So that's what people think of what a wormhole is.
Huh. I see. So a wormhole would basically be, the like first thought about it would be like 2 points distantly away from each other, or 2 points in space in different universes, and I'd be able to like go in through one and come out the other in like almost no time at all, as if I'd like loosely, not instantaneously be transported, but like moving faster than light of those 2 points because they're connected through this wormhole. Is that like at least the classical intuition behind it?
Right, kind of, but moving faster than light may or maybe not, but it's a place where you can travel in and out. That's interesting.
Gotcha.
Mm.
Gotcha. Mikey, if you happen to know, maybe shedding some light on the history of wormholes, or like, I mean, like, where did this idea come from? Like, it seems so interesting that it just like popped into someone's head that this object could exist.
I'm actually not too sharp on this history. Like, but from what I remember, like from the grad school days, is like about the history is like, people realize that there's these areas of space-time that are called black holes, right? There's areas where gravity can become so strong that space-time basically like um, bends so severely that in a sense it kind of breaks the space-time. Uh, and then I don't know. I guess some other folks realize that like if you have this literal break in space time, you could have like kind of a portal connecting two breaks in space time that would kind of cause you to be able to do things that seemingly violate the laws of known physics, like teleport from one place to another or one time to another. Um, so it's been the subject of much uncertainty, I think, in the physics community for most of its history. Although I think it's become much more sharp in the last like 10 years. But in that same vein, like in terms of science fiction, people just ran wild with it, right? The idea that you can just like go into a portal and appear in another place in a time is very appealing from a science fiction perspective. And I think it's a cool idea because it's actually like one of those ideas where um, we have a hard time separating science fiction from science fact, and that's why like intelligent people like Christopher Nolan can make a movie like Interstellar and talk about wormhole, describe a universe about wormholes where it kind of is consistent with what physicists, like working physicists, like perceive as what the truth could be like.
Yeah, one of our audience members saying Kip Thorne coined the term. That's why it shows up in Interstellar. So,
Yeah, I mean, actually, fun fact, like I ran into Kip Thorne at like a conference, and at that time, I guess he was just so giddy. He was just going around telling everybody that he's making a movie with like Chris Nolan, but Chris Nolan doesn't make a movie unless his brother John Nolan like has final say on the script. So he was talking about how they're kind of like butchering his idea, but he was just like really glad that I think in Kip Thorne's original version of Interstellar, there was like 6 wormholes and just all kinds of crazy stuff happening. But I think the artistry of Chris Nolan and his brother Jonathan really kind of packaged it into emotionally impactful representation of what relativity is about. So it's like a great story, I think.
very, very cool. So I guess like Tim, you had mentioned something about black holes and wormholes. Like they seem like two separate things. Like what do they have to, why are they connected to each other? Like black holes seem like these objects that like when something goes in, nothing can come out. I mean, at least based on like, when you first learn about them, at least classical general relativity and whatnot. And then wormholes seem like they can exist outside of black holes and you just be transported. Like what does this have to do with black holes?
Yeah, I think you're right that they are kind of technically potentially two distinct objects. But it's just that black hole gives you this opportunity, like Mikey was saying, because there's literally almost like a break in space time, and that's why you can kind of glue them. When there's a break, you can kind of glue the two different black holes together, and then create a wormhole. So black hole is kind of an opportunity for us to think about, um, wormholes much more seriously. And I guess the first example of a wormhole is what we call the Einstein-Rosen bridge, is technically coming from a black hole, and this is where this wormhole is not traversable. Like you cannot jump in from one end and escape to the other. You jump in one end of the black hole, you just die. Right, you hit the singularity. But what happens is two people can jump in from opposite ends of the black hole and kind of hang out, but then they'll eventually hit their doom. Right. So this is the first example, but people have kind of cooked up with, from the examples of black hole, come up with much more interesting scenario, and in some ways, the wormhole kind of has gone beyond a little bit of the kind of the typical black hole paradigm, and in some ways, you can kind of have things that allows you to kind of teleport from one end to another without it looking too much like black holes, although it is still somewhat related.
What do you mean by that? Like that sounds very open-ended, or I don't know, that sounds
Yeah, it is somewhat
compelling.
yeah, it is
Compelling.
somewhat open ended, and particularly it's coming from this proposal called the ER equals EPR conjecture, right? There's this conjecture that what we call quantum entanglement might just be wormholes. And without getting into too much details, the idea is that imagine you are going through a wormhole. You go from point A to point B, and from your point of view, you kind of just experience this kind of level of teleportation, so to speak, right? You kind of at point A, and somehow you feel like you go through this tunnel, whoop, and then you end up at point B. It turns out in quantum physics, we have things that are kind of like that. We have quantum teleportation possibility. You can send in these quantum mechanical objects, and kind of through quantum computers, you can kind of not instantaneously, but kind of move it really quickly from point A to point B, and these will be perfect copies. And in some sense, it's not a copy. You're literally moving quantum information from point A to point B, right? But imagine if you yourself are that quantum information. You're just feeling that you're going from point A to point B, right? Because in quantum information, you cannot copy information. Information has to be preserved. So in a very literal sense, imagine you are that quantum information. The fact that you got teleported from point A to point B is kind of like going to a wormhole, right? And this is kind of the fact that the discovery is hounding on that quantum teleportation, in a very real sense, may be a wormhole. And so, in that way, maybe we can build a kind of a miniature quantum teleporter, and maybe we can call that a wormhole.
Yeah, no, that is very interesting. I guess like question to either of you, can we shed more intuition for like our audience, like maybe a short like 30-second to 1 minute description of like what quantum entanglement is and like how's that related to like a wormhole? Like it seems like wormholes are these like classical objects that appear in general relativity, and then you have quantum mechanics, which is like a very small thing. So how can we say these two things are related, at least like at a super high level? How can one
Okay,
thing?
I can't answer your question, but like just to elucidate a little bit on it, and I might be butchering this because I don't know the history that well, but like I mean, just if I had to recreate what it was like to conceptualize the idea of a wormhole, it's almost like, hey, there's these like crazy objects called black holes. Hey, if I take two of them and stick them together, I can recreate, within the rules of Einstein's general relativity, I can create a mechanism by which you can essentially create a portal, right? So that's like on one hand, that's like one theory that's like within Einstein's general relativistic theory. And then as Tim was saying, on this other hand, you have this phenomenon in quantum mechanics where you can actually transmit quantum information from one point to another point that is seemingly, like too far away to be able to communicate such information. Um, and I don't know, correct me, I don't know, correct me if I'm wrong, but my impression is that like it's just like for Susskind and Maldacena who came up with the ER equals EPR idea, it's almost just a realization, hey, these two things have very similar properties. What if it's actually the same thing? And they worked out the logic of it like within the theoretical bounds of like quantum field theory, and they found that it's actually a very plausible idea that these two things could be actually two sides of the same coin. Not only that, but they found a lot of evidence to support the fact that these two things ought to be sort of two sides of the same coin. And that's sort of where we are right now. I don't think anyone can say that they have a great understanding of how this like wormhole correspondence to quantum information came about. But as most things in physics, it starts out with just noticing that two things have exactly the same properties, and then trying to bridge the gap between them, which is, I think, where the state is right now.
Yeah, yeah, and I think if you look at the properties of quantum entanglement, you will notice parallels. Like quantum entanglement can be thought of as this kind of spooky correlations, right? Like imagine you have a dice, you have a quantum dice here, on my left hand, and another quantum die, I guess, on my left hand, and a quantum die on my right hand, right? Quantum entanglement means that there's a way I can entangle them in such a way that the information is perfectly correlated. So basically, imagine if I roll my die on the left. Let's say I get one. The die on my right will also be. Let's say if I make it such a way that they're perfectly correlated, the die on my right will also get one. If I roll a two, the die on my right is also two, right? So on the one hand, I can think of them as quantum entanglement of two dice, right? And that there are two dice. Or on the other hand, I can be like, maybe there's a wormhole connecting them, and the fact that I have two hands is just, I'm just playing with different ends of a wormhole, right? And it might sound kind of ridiculous, but the outcome is the same. If there's two dice that are quantum that are perfectly entangled, I'll get this answer, right? They're perfectly correlated. Or if there's a wormhole, of course I play with it for my left hand. It's the same die, right? And I play with it for my right hand. Of course, I'll get the same answer. So that's why this kind of light up a light bulb in some of these brilliant physicists. They're like, hey, ding ding ding, maybe we're talking about the same thing. Like maybe these are two different descriptions of exactly the same physics.
So I want to ask you a kind of clarifying question to see how far I can push this analogy that you just gave, like between two, let's say two quantum die or two quantum coins or whatever objects that you want to use. And let's like take, so I understand the case where if they're both entangled, meaning this like perfect quantum correlation, you roll a one and with your right hand, you get a one on your left hand, and et cetera for all the other faces. Now, could I think of it in terms of the wormhole analogy as if like I roll the dice and then I get some number and I quickly toss it through the wormhole and then it appears on the other side, like not instantaneously, but like like just really like very quickly, and then it's as if that also has rolled on in my other hand.
Yeah,
Is that
basically, that is exactly the
Fair.
idea. That's exactly
Yeah.
the idea. Yeah.
okay? That makes a lot of sense. So it's so if what I'm understanding is it's unclear why these two are like connected at like a deep level, but there are just a lot of parallels between quantum entanglement and wormholes that people strongly believe that they are linked together. That this conjecture ER equals
Yeah.
EPR is taken seriously.
Right.
Is that correct?
Exactly. Yeah. Exactly.
Yeah. I will go
Mhm.
a little further than that. I mean, I'm not too up to date like in the literature with this, but I mean, like there's papers coming out all the time that are basically just compounding evidence for the fact that there is an equivalence for these two things, like
Mhm.
thought experiments, like things that have to be true for one interpretation also turn out to be true on the other side of the interpretation. So, nothing proven yet, but just a lot of like theoretical evidence accumulating for why these things should be similar.
Yeah. Yeah. And I would say most of these evidence are kind of like computational.
Mhm.
So you run a calculation on a computer and you check you. I mean, in some ways you're doing one calculation. You're doing 1 + 1 = 2 in many different ways, and you
Mhm.
show that you arrived at the same answer. So these are kind of like theoretical evidence, right?
Yeah, consistency checks.
Yeah, on consistency checks, and then coming back to the significance of this achievement by Team Google and many physicists. Um, this is, I would say, kind of the first experimental demonstration of this equivalence. That at least
It
so
looks like giving credit to Google. Let's keep
yeah,
calling this as the Google team. This is the
probably
Google
not.
team.
Well, they borrow
Google,
it
Google just let them borrow the
pretty
computers, right?
much.
This
Yeah,
is,
they got
yeah,
money. That's about it.
yeah.
It's mostly a physicist's achievement, I would say.
This is people that we know, we love, like Daniel Jaffrus, Joe Licken, like, just like very, very well-known, reputed,
Physicists.
particle
Yeah.
physicists. Yeah.
Yeah. So I guess now let's like come back to the original reason we started this conversation to understand this work. So I guess let's kind of start by saying like what was like factually the conclusion that they made and then kind of work on like what the setup was. So Tim or Mikey, I'll leave it to you to whoever.
Yeah. I.
Should
I
we phrase the question differently?
Yeah, ask away.
It's hard. I think the question you pose is harder to answer because, like, what did they actually achieve? That's kind of a murky question. I think
well,
the question that
I think we can kind of answer it because if you ignore all the hype and ignore everything, you can just go straight to the source. And if you look at the Nature paper, unfortunately, it's not very accessible to a lot of people. The title of the paper is called Traversable Wormhole Dynamics on a Quantum Processor. And I think that succinctly, summarized the achievement. They've
yes,
simulated traversable wormhole dynamics on a quantum processor. Like that is unambiguously true. And this is for the very first time.
okay, but you could ask I guess like most of the complaints about this paper have to do with like science outlets, science journalism outlets like overhyping it. I don't know. Let me go a little further. Like, did they actually make a wormhole? Like a worm? Did they make a wormhole?
I would
Wormhole and make.
I think there are two perspectives. I think for me, I would say no. And the reason is because when I say wormhole, I think 99%, probably more of at least the people in the world, when they think of wormhole, they really think of these, grandiose structures in space-time where you can travel. Okay? So these teams of physicists, they did not create that. And there is no way you can create that on a quantum processor. So by that logic, no, they did not create a wormhole. But is there another version of wormhole they have created? Now that's where it gets ambiguous.
I would. Okay, so maybe they didn't create the wormhole in the way that you described, like an actual, like whatever perfect wormhole. But I can guarantee you that, like, if 1,000 years from now, if we make a wormhole, they will cite this paper. Like that's really the bottom line, right?
Yeah, yeah, I can see that. Maybe, yeah, I
They
can
are
see that.
genuinely coming close. Like whether you agree whether or not it's like a exact perfect
Right.
wormhole, like they're taking a definite step towards the eventuality, the inevitable eventuality of humans creating universes and creating
Yeah.
wormholes in these universes.
It's like
Yeah.
the tiniest baby step of a baby step of a baby step, if ever.
But it's not so baby that it's like insignificant to be forgotten about. I really do think that like as this line of research evolves, like they're going to be like the techniques that they used to create this wormhole and the properties that they proved that this kind of toy cartoon wormhole has are non-trivial. Like those are things that are going to be cited,
Yeah, yeah,
I think, for
absolutely. I agree with you that it's non-trivial, and I would say that a lot of criticism on this paper comes with the fact that you actually don't need a quantum computer to simulate this. You could just pretend that this quantum computer is only a classical computer and just use a crap ton of server CPUs, maybe not even that, to actually run the calculation. But then keep in mind that look, physics is an experimental science. You can fake a quantum circuit, but it will never be a quantum circuit. So in some ways, sure, like you can classically simulate this, but you never guarantee that you get the same result on a quantum simulation. But then of course, some people argue that it's still a simulation. Like it's not literally a yeah, it's not literally what it is. So I guess yeah, there's some conflicting emotions there. So
Yeah. So I want to take a step back before we kind of dig deeper into this. So going to the title of the paper, simulating a like wormhole or like not the definition of what most people think of a wormhole, but this like different way of conceptualizing wormhole. Like, what does it mean to simulate? Like, can we dig into what that word means? Like, classical simulation versus quantum simulation. Like, what is that?
Yeah, I think that's okay. So, like, I would say that if they did this with a like, okay, so one of the big criticisms of this paper is that you could have just done this on a regular computer, right? You could have just taken any old desktop and you could have done the same calculation. You could have gotten the same results. Um,
Hmm.
and I would say that if we did that, that would be a simulation. But I think the fact that they did this with quantum materials makes it not a simulation. Um, I think it's honestly an actual wormhole in some sense of the word. Like the only way in which it's not an actual wormhole is because of the approximations they made. But I think that the fact that they're actually, it's like, what's a good analogy? It's like if you're making a cake and you make it out of like, like marbles, then that's like a fake cake, right?
Hmm.
But they actually took like delicious tasting stuff like sugar and they actually took that and used that to make the cake. I think the fact that they used a quantum computer to do this as opposed to a regular computer has some special significance because the materials you're using actually have the quantum properties that you're purporting to be simulating. And yeah, a lot of people criticize this because yeah, you could have just done this with a classic computer, but I don't know. I think the materials you use, like, it's kind of cheap, right? Because it's not harder to do this. It is harder, but it's not necessarily that much harder to do it on a quantum computer than a classical computer. But the fact that they did it on a quantum computer, I think, is like, they were just the first ones to do that, and I think that's a big deal.
Gotcha, gotcha. Tim, you were mentioning like that you could simulate this on a classical computer, but it wouldn't be the same as like doing quantum on simulating a quantum
Oh,
computer.
that's what I said.
Oh, that's what you said. All right.
that much we agree, I think.
I guess okay. So to Mikey, why is that not so? Like we have the laws of quantum mechanics. Like why can't I just simulate this on a classical and be done
It's
with it?
like it's like drawing a picture of a house versus like making a house with sticks. Like one of them is like a representation,
Yeah.
like in a medium that you have to use your imagination for to actually make the connection. But the other one is actually using the materials that you would use to make a house. So this is like a stick figure house. If an actual wormhole is like a house, this is
Hmm.
like a house made of like popsicle sticks. But that's better than a house like drawn on a piece of paper, right? Like even if it captures all the information, Like you're actually using the materials to make the structure, um,
Yeah, yeah,
and
yeah. I think the weird thing is that one has to keep in mind that in quantum computing, you are literally using the information itself to kind of build the operation. Unlike in classical physics. In classical physics, for example, you can copy and delete things. You can make copy of things, and there's always a little bit of sloppiness in it, kind of, right? And the reason why classical computer is kind of robust is because these zeros and ones are always approximations. Like, for example, your numbers always have finite precisions. Like you're never gonna really compute square root of two. It's only square root of two up to a certain number of digits, right? But quantum computer itself is different because when you have a single bit of quantum information, it has infinite precision. You can't
yeah,
you can't make a copy of it. You cannot delete it. So in a very real sense, when you kind of teleported that qubit from the left side to the right side, even though there might be noise in this quantum computer, in a very real sense, you kind of did teleport that stuff. Versus
yeah,
on a
exactly, yeah,
classical computer, yeah, you just copied like a many glorified ones and zeros, right? Even though it might look way prettier, it kind of isn't the same thing. So in that sense, if you kind of squint really hard, you kind of can think of this wormhole on a quantum computer as kind of a tiny little stick figure wormhole, like that. I think we can agree on.
yeah.
So so with a giant asterisk, probably larger than the word itself, then yeah, you could say that that's a wormhole. I would say.
Yeah. Just to expand on what Tim's saying, I think that's exactly right. Like with a classical computer, like if you were to do exactly the same calculation on a classical computer, you're still using wires to like represent the ones and zeros. But with a quantum computer, quantum computing is fundamentally exact. Like you're using the exact state of particles to do your computation. So you're actually representing exact states of particles to create the object that you're, purporting to simulate. And I think that's significant. It's much more real in a fundamental sense.
What one, I mean, more approximately, right? Because you still have like the environment to contend with that can muck up your system.
Yeah.
Sure, yeah, and you also have the fact that they had to take some of they didn't do the full theory because the computing power is not there yet, so they had to take an approximate version of the theory. There's all kinds of approximations, but still, the quantum does that sound the quantum nature of it is uh, is preserved in the calculation, and yeah, I don't know. To me, that means something. I think yeah, people could disagree about this, but to me, that really means something.
Yeah. And so one question our audience members have asked us is this evidence for ER equals EPR, what we had discussed before?
I don't think it's evidence for it because ER equals EPR is like, the theoretical underpinnings of that have been established. So it's, as Tim said, it's almost like if you do the experiment, you know what answer you're going to get.
Hmm.
Um, this is kind of like taking ER equals EPR and trying to make it real in some way, as opposed to just equations on a paper.
It's kind of like almost like a new category in itself, right? It's almost like a quantum engineering. How can I take
Yes.
how can I take these known pieces and create something out of it? And in a very real sense, they took the quantum information and they made kind of like a tiny theoretic stick figure wormhole out of it.
Hmm. Yeah. So we're almost at time. I guess like coming back to the question, like, is this hype? Is this like something we should take seriously or long way to go? I guess like Tim, I'll start off with you first.
I would say there's definitely hype. I mean, I read a lot of these, popular
That's way
science.
overblown, right?
Yeah, I think parts of it is way overblown. We did like we definitely did not create wormholes in the most conventional sense. It's not like you can jump into it and exit out in next to Andromeda or something, right? But a qubit, a tiny bit of quantum information did enter from one end of the chip and come out from the other end of the chip in some way. So from the perspective of that little qubit, it happily went through a stick figure wormhole, an approximate one at that. So so this is ultimately this is kind of like almost like a bit of a new category, right? This is kind of like quantum engineering esque mixed with physicist theorist achievement, and it's not like super groundbreaking, but I guess I would agree with Mikey that if there's a real wormhole in the distant future, yeah, they probably will cite this paper. So I'll give you that.
All right, Mikey, what do you have?
Yeah, I don't know. Maybe this is just for people who watch the movie Interstellar. But the idea that like if human evolution goes on and on and on and on, if we survive that long and we master the art of quantum computing and we actually learn how to create our own universes, and I guess essentially become gods. Um, I think this is a concrete step in that direction. Like, yeah, I'll just leave it at that.
Right then. I want to thank everybody for joining us, and we'll see you all next week.
Yeah, see you all next week.